Right. So I was still talking about aligning these beams, yes? Okay. So very similar to how we did it for the first set of beams. I'll just click OK. Material properties will stay the same. Sectional properties will stay the same. Orientation key points, keep selected. Click OK. And I'll select my orientation key point 30. Okay. So now we've oriented these beams and these beams to do different key points. What we could have done is I could have orientated these I could have drawn these beams, oriented them, and then copied. It would have done the same thing. That would have been even easier, more efficient. But just to show you that you can do multiple different key points for multiple different lines of beams, I've demonstrated it this way. So again, go to Mesh Tool. These lines, I'll divide them into sections of 10. So I will go line set, and all of these beams will have the same mesh. Click OK. Set the number of divisions to 10. OK again. Mesh. Yes, this second half I will record myself and post to YouTube. The first half I didn't record because I wasn't the host. So ITS will have to post the first half, but the second half I'll post myself. So I've applied the mesh to this member, and if we want to just check that we've oriented it correctly, we go to plot control, style, size, shape, turn this on, okay, and now you can see our I-beams still there, and our C channels. Oriented so that they're in line with the y-axis as well. Of course, if you wanted your C channels to be oriented how they were originally, in line with the z-axis, you wouldn't have to do any of that mesh attributes step. Okay, it's all up to how you want to orient the beams. For I-beams, you generally want to orient them so that the web is in line with the direction of the force, because it's strongest in that direction. But C channel, you could have oriented it the other way. It's fine. Right. Up until this point, I have demonstrated only with beams. I haven't done anything yet with a shell. So now I will do the shell section. Also make sure that it is not three-dimensional. Back to this. Right. Now I want to create individual shells, squares, or rectangles, sorry, 1 to 15, 14, 6, and then, so I will have 1, 2, 3, I'll have 12 rectangles. The reason that I won't do one big plate is because the software won't know that the plate is actually sitting on top of these key points. All right, do you get me? So if I were to model, if I were just to make one big plate going from 1 to 29 to 23 to 2, it would assume that there is nothing underneath it stopping it from deflecting downwards. Okay, it would just slope, big slope. Because we haven't actually told the software that this key point is connected to a beam which is underneath it, or a beam that is also connected to that key point. So we will break our plate according to the key points that are set up, the grid. This is a grid now. So a 3x4 grid. So I'll create one plate here, one plate here, one plate here, here, 12 plates, which will all be connected to each other at these different key nodes, these different key points, or these different nodes. So it'll act like a single beam that is being supported by all this structure underneath. So you guys doing bridges and billboards and all that, you have to bear that in mind. That if there's a structure behind it, you have to make sure that your plate is connected to that structure and it's not just sitting in free space, or it's not just connected at the far corners, because in reality, it's not connected at the far corners. It's supported by all the beams underneath. All right, so I will go to modeling, create areas, arbitrary, through key points. Now I'm going to go in a clockwise direction, meaning I go 1, 15, 14, 6, 6, 14, 11, 5, not go back and forth, because if you go back and forth in the opposite direction, your normals, your plate normals will be in different directions. Which means when we apply our pressure, if we go counterclockwise here and we apply a positive pressure, it'll be pushing up. And we don't want it to be pushing up, we want it to be pushing down, like someone standing on it. So if I go clockwise, that means my normal is on the top and it'll be applying downwards. Right, so I'll go 1, 15, 14, 6, apply, so on and so forth for the other. Clicking apply in between. Oh, sorry, this wasn't a 3x4 grid, it was a 3x3 grid, my bad. Notice that I'm going in a clockwise orientation, the way that I select my nodes. And the last one, I'll click OK. So now I've created all of my plate elements sitting on top of my beams. I have to assign a sectional property. So I have to give this a thickness. To do that, it's again done in meshing. So I'll go down to my meshing, mesh attributes. I'll go, you can either go picked areas and select all the areas, or you could have just gone and selected pick all areas. Done that, I click OK. Material property, this is material property 3. Type of element, it is a shell element. Section, 25 mm plate. Happy with that? There's no orientation for shell elements. Click OK. And now I can go to plot controls, settings, sorry, style, size, shape, turn on the 3D. And now you can see oh, I haven't actually meshed this plate yet. I've just given it material properties. So I'll go to mesh tool, areas. I'll pick all of my areas. Edge length, I will make, this is a 1.2 by 1.8. So if I divide it evenly and find a nice grid, if I break each length down into 30 centimeters or 0.3, I'll have whole numbers. You want to try and work with grids of whole numbers. If not, you'll start to have triangular elements introduced into your mesh, and you don't want that. So I will go 0.3. Okay. Mesh tool, mesh, all the areas, I'll pick all. Now I've applied my mesh, and you can also see that now my plate has a thickness. Okay, the reason that it's not sitting on top of the beams is because we haven't applied an offset. But for all of your projects, you don't have to worry about offsetting beams or offsetting plates, because it just gets a bit too confusing at that point. So if they look like this, that's fine. It'll just mean that our beam is connected to our plate, but it won't say how it's connected, just that it's connected, and that's good enough. All right, guys. So I have a 3-dimensional model now. I'll apply some boundary conditions. So I'm going to assume, well, I know that this point here and this point here is fully fixed because it's mounted to a wall. It's not a roller fix. So when I apply my boundary condition, I will fix in all degrees of freedom that point, those points. So now I can go to my meshing, my loads, apply structural displacement on key points. And I select my key points. Good thing about Ansys is it has a snap feature. So you don't have to actually click on the key point. It'll click close to it and it'll automatically snap to that key point. Happy with that? I'll fix it in all degrees of freedom, set the value to 0. Okay. So now I've fully fixed all of my supports and I can apply my gravity loads. The isometric view again. Now, go to loads, define loads, apply, structural, and inertia. Select inertia, and you can see that there is an option here, gravity. So I'll select gravity, and I won't select on components, I'll select global because the whole model is experiencing gravity. So I'll go global, and you set your value for gravity, which is 9.81. 9.81 meters per second squared. I click OK. You can see that there's an arrow here now. This just shows you that gravity is being applied in the y direction. When we actually solve, it'll be oriented the other way. So our gravity will be acting downwards. Going back to our question, just briefly, wait, just remember to save as decking 2, Ansys project. Right. So going briefly back to our question. So like I said here, the load should be able to support 5 people. Okay, we've already taken into account the weight of the materials. We've already used appropriate materials and sections. We haven't done this bit. It should be able to support 5 people. Now, what do you think would be the worst case scenario? Because we always try and design for the worst case scenario, yes? What do you think the worst case scenario is? Where do you think is the worst place for these 5 people to be standing? Is it spread out all along, so they're standing equal distance from each other? Should they be standing closer to the wall, closer to the support? Right in the middle? You think that's the worst case scenario? If they're standing right in the middle, then your bending moment won't be so much. What if they're standing right on the far side, on the far end? Right at the edge? Yes, that'll be the worst case scenario if they're standing in the middle and at the edge. Now, would they be standing all the way along the edge or just at one point? The worst case scenario you could possibly think of is if 5 people were piggybacking on top of each other or lifting each other up and standing in one point. That is the worst case scenario. That is the worst case scenario. So if we just designed it for 5 people standing equal distance along this edge, what happens if 2 people stand close to each other? The whole thing gonna fail. So you designed it so that even if there's 5 people standing very, very close to each other, it still won't fail. And you have to keep that in mind. What's the worst thing that could happen right now? That's the whole reason why when we're talking about trusses, we say that the worst deformation will happen at the center, at the distance in between the 2 supports. That's going to be the worst case scenario. So you always try and apply the maximum load at that worst place, the worst place for it to be, and design so that it's safe there, so that you know it'll be safe in any other way that you load it. Okay, so going back to our model. The worst case scenario, like I said, would be if all 5 people were standing in this small square here. In the middle, at the far edge. That's the worst case. Now, what's the area of this? So we know that 5 people, let's say that 5 people each weigh 120 kg. So that's 600 kilograms. Convert that to a force. That's 600 times 9.81 will give us 5,886 newtons. And we know that pressure, because we can only apply a pressure to this thing. If we apply a point force, that won't be accurate, or we won't be able to apply a point force to a plate or a shell element. Okay, it'll start to deform the whole thing unproportionally. So we'll apply a face pressure instead. We'll apply a pressure downwards. So that's our force divided by the area of that plate. So this plate is 1.8 by 1.2. So that'll give us a pressure value of 2,725 pascals. You following me? Following what I mean? So this is how you guys would go about applying your loads. If you guys are designing a bridge or a billboard or the crane even. The crane, you probably wouldn't have any plate elements. You just have all beams. So you just apply like a UDL or a point force. If it's a truss structure, you can apply point force. Point force is the worst case scenario. So for you guys, a point force would be worse. But if your design involves plates as well as beams, it's probably best to apply a face pressure. So in this case, we'll apply a pressure. So pressure on areas, I'll select this area. Okay. And I'll enter my value. My value that I calculated was 2,725 pascals. Okay. This might look like a jumble of lines and all, but it's actually being applied downwards. So now I can go and solve. I won't do all the post-processing and stuff because that's up to you guys to try and interpret. That is your assignment after all. So I'll go solution, solve current linear loading system. Okay. Solution done, no errors, no complications, no warnings. So we're sweet. General post-processor. And I'll go plot results. I'll make sure I read results first. Make sure you always read results from last set. If not, the solver won't know, the result interpreter won't know what results you're referencing. So you have to tell it we're actually talking about the results that we just solved for. Plot results, deform shape. I want to go deform shape only. And now you can see the effect of gravity means that there's load being applied all over the model because of its weight. But the worst case, it's bending right here. That's where we've applied our pressure. And you can also go to element solution, von Mises stress, and you can see the stress hotspots. We have stress hotspots, and it's telling us that the maximum stress that we're going to experience is 165 times 10 to the power of 6. So, oh, sorry, this is actually 16.5 megapascals. That's the maximum stress that we're experiencing, which isn't that much. If you then can compare this to the yield strength of the steel that we're using. So you can also get that property from MatWeb. So this is mild steel. I think mild steel has a yield strength of 200 and something megapascals. And this is 16. So right now, this is more than safe. You can also display the nodal solution. Yeah. Lots of different ways you can go about it. Maximum stress, the minimum stress, the maximum deflection. This is what, 9 millimeters, the maximum deflection. You could display, instead of stress, we can go we'll go deflection in the Y direction. Mechanical strain, which is change in length. Y component of mechanical strain. You can say our highest value, 9.77. It's occurring somewhere around here, which we would expect because we have our pressure being applied. There's lots of different cool things that you can extract from your results. But I want to remind you that just doing this one time isn't enough, okay? So we've done it once and we found that using these sectional beams, and using, the sizes that we have way over designed this model. So if you were to go back, we could then change some of the sectional properties, apply different sections, simply just change the material section and then solve it again and see if we can get, use less material, get a better factor of safety. Right now, the factor of safety is around like 20. That's way too high for something like this. Maybe you'd be looking at a factor of safety of like 2. So then you can start to refine your design, refine your model. And that's what the assignment's all about, using finite element analysis to help you decide what is your best design that you can go for. Okay, guys, any questions? Well, I mean, there must be a lot of questions, but I'll upload this second part right now. And hopefully the first part is uploaded by ITS by the end of the day so that you can have a look at that. And like I said, please, if you have any questions, tomorrow I'll be running this lab session again from 5 to 8, doing the same activity. Is the offset command hard? It's a bit confusing because you have to know what face is positive, what face is negative for these shell elements. And trying to, in this case, the offset won't change anything. Like it won't change any of the forces that's being experienced by this model. Because we're working with very simple elements, so we're working with just beams, we're not working with any solid elements, we're not working with any like brick or plate elements. We're not defining any contacts between surfaces. So this is just a very simple model, which is what we're expecting from you guys at this level. Just simple models, beams and shells are fine. We don't have to actually start offsetting and applying contact surfaces and stuff like that. Because as well as doing this, there's also a hand calculation verification stage, which I think maybe Jiganda will explain in his lab session, which is running from 11 to 2. So if you join his session, he might be able to help you there. But if not, thank you very much for attending this morning. I hope this hasn't discouraged you. I hope it's shown you the possibilities of Ansys Mechanical, APDL, and I look forward to seeing your projects and assignments. The link, do you want me to send it to the Viber group or are you already I'll send the link to the Viber group just so you can have a look from there. Make it easier for you guys.
Thank you, sir.
So, no, guys, have a blessed day.